Need experimentalists like Zahid.
Yeah, we need lots of experiments, and our our researchers, students will get inspired to start work on it. Thank you very much for your very interesting talk.
Thank you.
Thank you. We shall now move over to our final talk of the plenary lectures, and this is no other than Professor Eric Cornell. Professor Eric Cornell was born in California and had schooling at San Francisco Lowell High School. After high school, he enrolled at Stanford University and graduated with honors and distinction graduated with honors and distinctions in 1985. He did his PhD from MIT. After obtaining his doctorate, he joined Carl Wieman at the University of Colorado Boulder as a postdoctoral researcher on a small laser coding experiment. During this time, he came up with a plan to combine laser cooling and evaporative cooling in a magnetic trap to create a Bose-Einstein condensate. For synthesizing the first Bose-Einstein condensate in 1995, Cornell, Wieman, and Wolfgang Ketterle shared Nobel Prize in Physics in 2001. He is currently a professor at the University of Colorado Boulder and a physicist at the United States Department of Commerce and National Institute of Standards and Technology. He was awarded the Lawrence Medal in 1998 and is a fellow of the American Association for the Advancement of Science. He was elected a fellow of the American Academy of Arts and Sciences in 2005. Eric Cornell received multiple awards, including Nobel Prize in Physics in 2001. There is a long list of medals and awards Eric Cornell received. We are not going to mention all of them to save time, but he is an outstanding physicist of our time. Now we are very happy to let Professor Eric Cornell give us the lecture. The floor is yours, Professor Eric.
Okay, Cornell. Thank you very much.
It's yours.
Are people able to hear me?
Yes.
Okay, then I will share my screen.
Yes, we can hear you.
Okay. Okay, it's a great pleasure. My real regret is I wish very much that I were there in Bangladesh, where I have a long way to go. And this is, of course, like the entire world, we accept second best, and second best right now is my house. So I'm sorry not to be there, but I'm very happy to be discussing with you. My understanding is that this talk will be shared around Bangladesh, and people of very different ages and backgrounds will be watching it. And I will try to include something for everybody, you know. And so I realize that some people may be hoping to see a technical talk, some people may be hoping to see some historical background, who knows? And I can't, so if the part of the talk that you're listening to is not to your liking, please stick around a little longer and maybe you'll get to a different part of the talk. I'm going to be talking about something called Bose-Einstein condensation, which occurs at extraordinarily low temperatures. Temperatures down, which we measure in degrees Kelvin, which is to say degrees above absolute zero, and in our case, nanokelvin. So the lowest temperatures in this picture correspond to 50 over a billion, you know, 5 times 10 to the minus 8 degrees Kelvin above absolute zero. Before I get into describing how these things are made, I was going to do a little history, which I think might be particularly interesting. It's a little bit, you should be wary of hearing history from a physicist. I'm not a historian, and I'm talking about things which occurred roughly 100 years ago. And these are my impressions of the history. You should not take them seriously as serious history. The sort of point of departure I'm going to use is the spectrum of black body radiation. It can illuminate much of the history, and I put a little asterisk there because, as I say, it's a physicist's history. It's not a true historian's history of 20th century physics, especially quantum mechanics and statistical mechanics. This is a conception of an iron pot, which has become hotter and hotter, and it becomes hotter and hotter as temperature changes from red to orange to yellow. And even at the highest temperatures, a little bit of blue color at extraordinarily high temperatures. And explaining, coming to explain the natures of these colors and the spectrum of these colors drove many of the developments, important developments of physics. And we'll be hearing about some of the great names of physics, including Maxwell, Planck, Einstein, and the great Bengali physicist Satyendranath Bose. If we look at just a little region of this pot and we look at the color coming out from it, we see it's not a single color, but a combination of many colors, including red and blue. And there's a black body radiation spectrum, which sort of says we see so much at the bluest and so much intermediate and so much at the redder color. And the shape of this curve is a complicated shape, and explaining it explains a lot. Max Planck, in the early part of the 20th century, came up with a formula that explained it. And that formula had different parts to it, but at the lowest frequencies of light, which we understand to be the longest wavelengths of light, or the reddest colors, we find that the spectral intensity is scaling as the frequency to the third power, nu cubed. How can we understand that? Well, we can really understand this from the equal partition theorem and from classical physics. The electromagnetic, dating back to Maxwell, there's electromagnetic waves. These waves are we put these waves inside a box, and there are allowed levels. We can think of these levels as being quantized because they could have 1 wave, 2 waves, 3 waves, 4 waves. The levels are quantized, but this is not yet quantum mechanics. This is classical quantization. And what we find is that as we go to shorter and shorter wavelength, or higher and higher frequencies, there are more and more modes available, and fewer modes at lower wavelengths or lower frequencies. And this is the origin then of this frequency dependence nu cubed. It just has to do with the phase space density of the quantized modes. So that part of Planck's formula could be understood reasonably well even in 1900, perhaps. But then if we look at the high frequency, the purple ultraviolet end, we see that it's decaying as this exponential with the frequency, a strong power of the frequency, the intensity is decaying. How do we understand that? Planck said, well, we'll say that for each of these spatial modes, we ask how much electric field is in, how much energy is in each of these spectral modes. And he postulated that the energy in each of these modes was itself quantized. Basically you could think of the electric field as coming in discrete units of amplitude, small, medium, large, larger, and larger, corresponding to what he called quanta of electromagnetic energy, and what later we came to understand as photons. And when you do the statistical mechanics of this, you get this high energy tail. So every single one of these spatial modes has a certain number of thermally determined photons or quanta of electromagnetic energy. Together, that explains black body radiation. And so things stood up through the 1920s. Then, shortly, right around then, about roughly 1921. I should also say that this notion of quanta, Albert Einstein took it a little further and said, maybe this is not just a mathematical trick, a way of accounting, not merely a way of sort of accounting for black body spectra, but maybe these quanta are real. And indeed, he explained the photoelectric effect, where light hits a surface and kicks out electrons of very specific energies. He explained this with the idea that the light is indeed physically coming in little packets, quanta or photons. This was the first evidence for photons. So, okay, so I have some words here that say the same thing. Then the Bengali physicist, Satyendranath, at that time he was a reader at the University of Dhaka, set out to explain black body radiation in what was in the 1920s understood as a very modern point of view. Instead of thinking about the electromagnetic field and thermal energy in the electromagnetic waves, he said, let us think of black body radiation as a gas, gas of particles, and those particles are photons. And we'll do statistical mechanics on the particles of photons and see if we can explain the spectrum of black body radiation as a sort of thermal distribution of high energy photons and low energy photons. And instead of thinking of standing waves of light inside a box, inside some volume, say with conducting walls, to get that spatial quantization, to get the phase space density, he used this very modern idea, which was of currency at the time of a phase space density, a little box of some small volume delta x cubed to delta p cubed, where the volume and phase space density is given by Planck's constant cubed. And so the question you want to ask is, for a given temperature, what is the thermal equilibrium distribution of photons in these boxes? And statistical calculations like this require one to count the number of distinct configurations if you want to get the respective probabilities correct. So you ask yourself the question, suppose I have two little boxes in phase space. These are little boxes of volume h cubed, and they say they correspond to the same particle energy, so there's no Boltzmann factor to take into account. Which is it? And suppose we have two particles that we wish to distribute among these boxes, which is more likely that we find two particles in box A, or one particle in box A and one particle in box B. Suppose we use what was then the sort of standard way of calculating this. Imagine that the particles came with names, Hank and Sally, you know, Ollie and Vasant. I mean, whatever you want to say, they have their names. What are the we'll call them beep and boop in this case. We see that there's one way in which we can put the particles in box A, and one way in which we can put both particles in box 2, but two different ways in which we can put one particle in each. And so based on this, we would conclude wrongly that it is twice as likely statistically to have one particle in each box compared to having two particles in box A. What Bose realized is that if he did that, and he went through the procedures of statistical mechanics and minimized the free energy, he would not get the experimentally observed, he would not get the experimentally observed black body spectrum. Instead, what he did is, let's imagine these particles don't have names. They aren't Frank and Sally. They aren't Ali and Vasant. They're all the same. We won't call them beep and boop. We'll call them both beep, and we can't tell them apart. And so then when he set out to just look at the different ways, these two ways are the same thing. If these particles are distinguishable, there's only one. Describing these as two different ways is incorrect. There's one way to put two particles in A, one way to put one particle in each, and one way to put two particles in B. And this way of counting things became known. First of all, it gave Bose the right answer, for the experimentally correct answer for black body radiation. And this way of counting became known as Bose statistics. And later, particles which obeyed the statistics became called bosons in his honor. And we should think of, okay, what's a factor of 2? A factor of 2 is a detail, but if suppose you haven't said 100 particles, and you want to ask yourselves the relative probability of finding 100 particles in box A and 0 in box B, or 50A and 50 in B. Bose statistics predicts that these two configurations are equally likely, whereas if these particles were given 100 distinct names, if they were all distinguishable one from the other, which is what's called Maxwell-Boltzmann statistics, we would instead find it is 10 to the 30 times inconceivably more likely to find 50 particles in each than 101 and 0 in the other. Bose statistics is not a minor statistical detail. It has an immense effect on physics. When Bose sent this paper to Einstein arranged it to be translated into German, and Einstein also continued to work, extended the work to the case where the particles are conserved. Like conserved, it means like they're not constantly being created and destroyed. In other words, like atoms and not like photons. And he predicted that if atoms would follow Bose statistics, there would be, you would observe at very high phase space density, which is to say low temperature, a sudden transition to a new phase of matter. I've sort of conceptually imagined that I'm keeping all my particles in a box. In this case, it's more like a bowl. And I've arranged these little boxes here to represent, these little tiny boxes to represent phase space density, little boxes of delta X and delta P cubed that atoms can live in. And as we go to higher and higher energy, there are more and more particles like that. Okay, no problem with that. But what Bose predicted is that if you put a bunch of particles and distribute them among these boxes, and then gradually lower the temperature, if we look at the number of particles which appear in the lowest energy box, and as we lower the temperature, we come to a critical temperature, and suddenly a very large number of particles appear in the box. And I've sort of characterized them by 10 to the 23. I don't literally mean 10 to the 23. It's just meant to be a typical macroscopic number, something like a bowl. Basically, all of the particles in your macroscopic system accumulate in this lowest phase-space energy box. And a very dramatic prediction. And I should emphasize that this is not an effect of brute force cooling. It would make sense that, like, if you were to lower the temperature so that the temperature KT is only the spacing between these two boxes, the lowest energy state allowed in your chamber to the second lowest energy state, it would make sense that just by brute force you would cool all the atoms into the lowest state because there wouldn't be enough thermal energy to go in there. But in fact, this critical temperature TC occurs at a temperature, this is dramatically not the scale, at a temperature which is much, much larger than the spacing between modes, the energy spacing between the macroscopic modes within the box you're holding in. So this is somehow a collective quantum effect. This was predicted essentially from the work of Bose and Einstein in 1925. 70 years went by and no one was able to confirm this prediction in the lab. So I'm going to try to explain to you why it was hard, why it was difficult for people to see this, why no one saw this for 70 years after the original prediction. Bose-Einstein condensation happens when the interatomic spacing, the sort of the density is high, so the mean spacing becomes small and becomes comparable to the thermal de Broglie wavelength, the sort of little thermal uncertainty in the location of an atom associated with its being at finite temperature. So if we plot temperature on this axis and density on this axis, we need to be at low temperature and high density to get to this region where the interatomic spacing is less than the thermal de Broglie wavelength. So in this log-log plot, there's some sort of curve, and down here is Bose-Einstein condensation, and up here is not. I've included no units on this because it depends, everything depends on the temperatures and the densities and the masses of the particles, but this is how it scales. Here's another plot, and this sort of represents much of classical thermodynamics. Again, we have a density on this axis and temperature on this axis, and we take some material, say water or anything really, at high densities at low densities and high temperatures, it's a gas. At high densities and low temperatures, it's a solid. There's an intermediate regime, but there's a very wide range of densities and temperatures which are forbidden, which is to say you never find material in this. So imagine an example is, suppose the material we care about is water, H2O. And here is, this purple thing is at 20 degrees Celsius and the density is at 10% of the normal density of liquid water. That's in the forbidden region. You can't make water. It's impossible to construct water at that temperature, at that density and temperature. If you were to take a can and fill the can 10% full of water and put the lid on and have it at room temperature and shake up the can and then look inside, you would not see water like this. Instead, on the lower 10% of the can, you would see over here high density water, and for the upper 90% of the can, you would see over here low density gas, but nothing in this intermediate region which is forbidden. Why does this matter? Because it turns out that no matter what material you work with, I don't care if it's, you know, any physical material we know about, if we put these two plots together, we find out that BEC occurs below this line, which is in the classically forbidden region, except if you go to high enough density where things are solid. And it turns out that solidification is the enemy of Bose-Einstein condensation, because once we have a solid, you may have seen these amazing photographs where the scanning microscopic tip goes in and identifies each atom. Once you have a solid, the atoms are no longer indistinguishable. You can identify them by their location in the crystalline solid lattice. And it turns out, just as a nature of any sort of material we know about, it just turns out that to be at this high enough phase space density, it forms a solid. The only exception is liquid helium. Liquid is not a solid, it's a liquid. So indeed, it is predicted that liquid helium has properties which are much like a Bose-Einstein condensation, but experimentally, one can't readily observe that it is a Bose-Einstein condensation. Okay, historically, okay, but I should mention that you might think, okay, well, this is going to be a very short talk because this plot tells us that you can't make Bose-Einstein condensation. The answer is, if we go to very, very low densities, we could start with a gas here, and we can cool the gas out of the gas region into the forbidden region and all the way down to become a Bose-Einstein condensate. And it becomes a Bose-Einstein condensate not in true thermal equilibrium. It's in a metastable state. The chemist would say it's supersaturated. You know, if you take a very, very hot water, you can dissolve a lot of salt in it. And as you cool the water down, the salt becomes supersaturated, but it doesn't instantaneously form salt crystals. It takes a while. Similarly, if you take a gas of water vapor and cool it into the region where it should be water droplets instead of water vapor, you don't instantly get clouds. The clouds have to nucleate around a little piece of dust. Or you can take any gas and cool it, in some cases, in our cases, we cool it 11 orders of magnitude below the temperature at which it should liquefy down into the region. So it's very, 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 very supersaturated. But as long as we keep the density very low, it cannot spontaneously form droplets or crystals. But if we want to be at very low density, this plot tells us we have to be at very low temperatures. And this is why no one saw Bose-Einstein condensation for 70 years, because the temperatures involved were spectacularly low, something far below 1 Kelvin, which was not really possible with the technology of the day in the 1920s, or 30s, or 40s, or 50s, or 60s, or 70s. It was really in the 1980s that people started to think about doing these experiments with gases of hydrogen, as it turned out in those days. Experiments in Amsterdam and MIT University, Cornell University, University of British Columbia, using not the molecular hydrogen, but atomic hydrogen in dilution refrigerators. And in the 1980s, dilution refrigerators were the most advanced form of refrigeration. Not good enough, as it turned out. So for some 15 years, people tried to do this and it did not succeed. But then along came this idea called laser cooling, an idea which came out of atomic physics. And I'll tell you now more about experiments which are done in my lab, often, usually with my collaborator, Professor Carl Wyman, with whom I collaborated for 15 years. And then with many students and postdocs and undergraduates. We'll meet some of them later. I wish I could tell you that I invented the technique of laser cooling. It's a very, very clever idea of using the force photons from a laser beam carry not only energy but also momentum. And if the laser beam bounces off of an atom, here you can sort of see conceptually these tiny little photons bouncing off of a much larger atom. It's an artist's conception, but they carry energy but also momentum, and the force of this laser hitting the atom will change its velocity. And if you can arrange to have your laser beam change the velocity in the downward direction to reduce if you have a gas of atoms, and you can reduce the velocity of all the atoms using an effect called laser optical molasses, you can get to extraordinarily low temperatures. I did not invent this idea. I wish I did. It's a really clever idea, but it was in fact the subject of two other Nobel Prizes. You can also bring in the laser beams from the north, the south, the east, the west, up and down in 6 directions, and use them to push the atoms into a little ball and cool them to very low temperatures. Something less than a millikelvin, something less than 1,000th of a degree above absolute zero. It turned out this temperature was still not low enough, even though at the time laser cooling was the hottest thing in cold, still not cold enough to see Bose-Einstein condensation. So we went to yet another form of evaporation, which was called another form of cooling, which was called evaporation. We put the atoms effectively into a magnetic bowl, and we let the atoms roll around inside this bowl, and the hottest atoms were allowed to come out to the edge of the bowl and come over the edge of the bowl and fall out. And when this happened, they took with them more than their fair share of energy. You can see that the atom that's leaving here is the only atoms that can leave are atoms which have much more than the average energy of the atoms in this bowl. So when an atom leaves, the average energy of the remaining atoms goes down. They get colder. And if you are confining them in a bowl with a round bottom like this, instead of like a cup would have a square shape on the bottom. But if you have instead a bowl, as the atoms get cooler, they settle down into the center of this bowl, and their spatial volume becomes smaller. So it's possible to throw atoms out and yet have the density of the remaining atoms go up and the temperature go down. Higher density, lower temperature, more phase space density, the direction we want to go to make Bose-Einstein condensation. This is very analogous to the laser cooling of, well, in this case, my morning cup of tea. Earlier, when it was hotter, you could see steam coming from the top of the tea, and that steam was the water vapor. And the water vapor, in turn, was the most energetic water molecules breaking free from the confining surface of the liquid water and carrying with them more than their fair share of energy. And the temperature of the tea went down very quickly, close to absolute zero by now, so no longer drinkable. And this is the effect of evaporation. It can become very efficient. It's hard to get, you don't actually get to absolute zero if you don't drink your tea. And that's because by the time you get down to 15 Celsius, something like that, there are no more, basically there's no more water molecules with enough energy to break free of the work function, of the surface tension that holds the water together. So the rate of evaporation essentially vanishes. In these magnetic traps we make that hold the atoms, we can adjust the height of the bowl, and as the atoms get colder and colder, we can lower the lip of the bowl. It's kind of like taking a cup of water and dialing down the surface tension. If somehow we could reach in a knob and turn a knob on the side of this cup that dialed down the work function, the tension that holds the water together, it would indeed cool and keep cooling all the way down in principle to absolute zero. And that's what happens to the atoms. They get to extraordinarily low temperatures. The whole system is put together into an integrated, there's a box with extraordinarily good vacuum inside. We have basically up towards the top here, there's a whole room almost full of vacuum pumps. So this is like a vacuum flask that keeps everything inside cold. And only the atoms themselves are cold. The wall of the chamber is at room temperature, say 300 Kelvin, more or less. People who come to visit my lab are sometimes disappointed because they expect to see something like world record low temperatures, and they want to see bubbling fumes of liquid nitrogen and liquid helium, and frost on the side of the chamber. They want it to look cold, and it doesn't look cold because the glass and the magnets and the laser beams, none of these things are cold. Only the atoms themselves get cold. Here's a more realistic look of the experiment. There's this is a glass window, and here's the vacuum chamber. That disc there, it looks like an idli, and that is a magnet. The diameter of this window, just for a sense of scale, is 2.54 centimeters, or as we say in the US, 1 inch, to the immense embarrassment of those of us who work for the National Institute of Standards and Technology. We would like to tell you this is 2.5 centimeters, but we're a little backward. It gives you a sense of the scale. The laser beams that come in and cool it, then we turn on the magnets and do the evaporation. And then let's see if you can see it here. Here is a lens. This lens is a lens we use for taking a picture of the atoms. And we use pictures of atoms to measure their temperature. We basically can tell how hot they are by taking a photograph. Here's conceptually that laser beam coming through the atoms. The atoms absorb a little bit of the light. There's a shadow. and that shadow is formed, is imaged onto a CCD, basically onto a digital camera. How does that tell us what temperature it is? Here is I show this data for historical reasons. Back in the 1990s, memory was quite expensive, and we didn't have enough memory in our computer to store a lot of images, and so we only sort of kept the centralized strip of the photograph. Well, that's the only part that we stored. And you can see in this image the cloud. This is a negative image, so you see this sort of large cloud of atoms. Remember, the atoms are being held in a sort of magnetic bowl. If we know the size of the atoms, we know how far the individual atoms are rolling up the side of the ball, and we know the curvature of the bowl. So if we know the size of the cloud, we know the energy of the atoms. This cloud is at 20 microkelvin, 20 millionths of a degree above absolute zero. At that time, close to a world record, but not nearly cold enough. We then continued the evaporation, let more and more atoms fall out. The cloud became a factor of 10 smaller in distance. This is a parabolic bowl, so a factor of 10 smaller in distance is a factor of 100 less energy. So we've come from 20 microkelvin down to 200 nanokelvin. This cloud is about ready to Bose condense. We went to, I took the group to an American Physical Society meeting in 1995, right before we were able to see Bose-Einstein condensation. And at the conference, we showed this cloud, and we showed this cloud. The older people in the audience will remember, before there were laptop computers, there were overhead projectors. You would copy your images onto a piece of acetate, lay the acetate on the projector, and the image. And you would do animation. The way you would do animation is you would have a piece of paper, opaque paper, on top of your transparency, and you would gradually move the piece of paper downward, revealing more and more data. And naturally, you would pause here. This is 180 nanokelvin. This is 35 nanokelvin, and you leave the little piece of paper here showing there's a little bit left of the image, in order to annoy your audience or to titillate them, whichever happens first. This is in 1995. I'll show the next image. You can see pictures of these diffraction rings. What that tells you is we're taking a picture of something which is smaller than the resolution image of our camera, which means smaller than this thing, therefore colder than 35 nanokelvin. Certainly at that time, by far the coldest thing ever seen, but we didn't have evidence that there was in fact a Bose-Einstein condensate in the center. So we went home from this conference. We thought of this conference, this was in 1995. My group we had been presenting this idea of using laser cooling and evaporative cooling as a way to make Bose-Einstein condensation. We thought it would be a moment of great triumph, because people would have to acknowledge that although we hadn't seen Bose-Einstein condensation yet, we had seen the world's coldest temperatures. But in fact, there were several other groups at that conference who were using similar techniques, including Wolfgang Kaderle at MIT, and they also had evaporative cooling. And we realized that we went more or less directly from people saying this idea will never work to many people trying to make the idea work faster than us. So we on the flight home, on the airplane home from the conference, my postdoc Mike Anderson said to me, I really don't think there's much time left for us to fool around in the lab. I said, no, there is not enough time left to fool around. And if you have been fooling around in the lab, this is the time to stop. It was a very tense moment. But we, as soon as we got home, we had the idea of suddenly turning off the magnetic bowl, letting the atoms fly apart. And when the atoms fly apart, the higher energy atoms have more velocity and they fly further apart, and the lower energy atoms stay in the middle. When we take a picture of this cloud, it's much bigger than the cloud was when it was in the trap, so it's easier for us to take a picture of. And basically, this picture is a picture of the velocity distribution. And as soon as we did this, we took pictures much like this within a few days after we returned from the conference. This is a cloud which is cold, but not quite cold enough to Bose-Einstein condensate. And from its size, this is the velocity. This is really the images are grayscale images, but we made them look fancier, more beautiful by presenting them as a 3D image with color as well. But imagine these are basically just grayscale images. But this size tells us that the temperature is about 400 nanokelvin. The existence of this shark fin in the middle here tells us that the condensate is starting to form. A little colder yet, and we have a pure condensate. All the atoms are in that lowest box inside the phase space density. not necessarily so small in coordinate space, but very, very low momentum. And so that's why they linger at the center of the image even after we've turned off the trap. You can think of this as a cup of water. This is a cup of water with an ice cube forming in it, and this is just the ice cube. Except instead of going from liquid to solid, you're going from gas to Bose-Einstein condensed gas, a new phase of matter. This is the group of people who were in the lab in 1995. This is Mike Anderson. Mike Anderson, an American man, but of Swedish descent. And people always sort of associate Swedes with being very beautiful, but in fact, maybe their most single notable feature as a nation is that they're serious. And so you can see here a very small smile on Mike Anderson's face. This was right after we saw Bose-Einstein condensation. For Mike, this is like hysterical laughter. The other people in the lab, Jason Ensher, Mike Matthews, Debbie Jin, are more conventionally happy about the results. 6 years later, these people have all gone on to different stages in their career, but we reconvened in Stockholm. Here we are dressed up shortly before going to the Nobel banquet. You can see Mike Anderson has regained his usual composure. The smile has had 6 years to fade. Just a little of the scene. Stockholm is a beautiful city, and particularly it's very beautiful around the time of the Christmas holidays. There's lights everywhere. It's dark because it's very far north, but they compensate for that by having lights and trees, and the city is next to water, and so you can see the light reflecting off of the water everywhere. It was a very exciting time to be there. I was there in Stockholm with many people from my lab, sort of as my entourage, but also all the other Nobel winners. There's Carl Wieman, who won the Nobel Prize that year, and there's Wolfgang Ketterle. Wolfgang Ketterle and I and Carl shared in physics, but there's chemists and economists and literature people all. And what are we doing here? We're in the hall where the Nobel Prize is to be presented, and we're having a rehearsal. We're practicing how to receive the medal from the king. And you might think that getting the medal from the king is not so complicated. And we did practice it, and most of us felt this was a little insulting. I mean, we were famous scientists. Surely we should be able to get the medal from the king. But it turns out that I was not able to do this effectively. I screwed it up. Here is the King of Sweden is presenting the diploma, and the medal is on top of it. And I am reaching underneath of the diploma to shake his hand, and he is reaching over the top. And then I don't have a picture, but 3 seconds later, he reaches underneath, and I reach over the top. And we can't come to an agreement about this, but finally we do. But meanwhile, I've tilted this back, and the medal, which I'm pleased to tell you is quite heavy, it's made of gold, starts to slide off of the diploma. And the king becomes worried. He says, that is going to fall on your toe. But fortunately, it did not fall on my toe. But the whole experience had left me so rattled that afterwards, I neglected the extensive protocol associated with encountering the king. And after I received the medal, I was supposed to bow to him. I forgot to bow to him. I just went and sat down. And as soon as I sat down, I realized, oh no, I've completely forgotten the protocol. As it turned out, I was the first person to receive it because my name is alphabetically before Wolfgang Ketterle, and I thought, well, maybe Wolfgang Ketterle will also forget, and people will just imagine this is the right way to do it. But in fact, Wolfgang Ketterle does essentially everything perfectly, and you can see he reached over the top, as did the king, and his bow was meticulous and perfect. So, oh well. Later, I'm very fortunate to have a charming wife, and we met for a banquet with the royal family, and my wife Celeste managed to smooth things over with the king. I think we're on good terms. Later, I was talking to the queen, and I was going like, these people who want to abolish the monarchy, they make me so angry. She thought that was great. But let me go back to Bose-Einstein condensation. So what is it like? These samples are small. Fewer than, if you were a chemist, you would say the sample of Bose-Einstein condensation is only a femtogram, perhaps 10 million atoms. The temperatures are 1 million times colder than liquid helium. The density is very low. It's a gas, but it's about 1 million times. Oh, someone has raised a hand. I don't know how to handle that. If someone is able to transmit a question, I'm happy to hear, but I don't see the chat. the density is much less than air, perhaps 1,000,000 times less than air. Even though it's a very, very tenuous gas, you know, you move your hand, you can feel the gas of air in front of you, but the condensate's 1,000,000 times less dense. Even so, because it's so cold, its texture is gelatinous, like aspic, like gelatin. We did experiments on this. This is one of the very first experiments we did. We took the magnetic trap and we squeezed it a few times and we let go, and then the condensate did a sort of, you can see over the course of about 5 milliseconds, it underwent sort of a breathing motion, and from this we could deduce its texture. In those days, we had a very small number of atoms, so you can see the signal to noise of these images is not great. Other properties of the Bose-Einstein condensate, it's coherent. Basically, all of the atoms are participating in the same quantum wave. The atoms are like photons, both are bosons, and just as lasers have all the photons participating in exactly the same wave, all the atoms of the condensate are participating in the exact same matter wave, macroscopically occupied, like a laser field. And then the sad thing about these things is that they're mortal. They don't live very long. Earlier on, I told you that we had to cool deep into the forbidden region of phase space to make these things. It's possible to do things which are forbidden, but you can't get away with them for very long. Eventually, nature says, no, this is not right. You should not be a gas at this temperature. You should be a solid. And so the gas decays into little snowflakes, essentially. And so typically condensates live for something less than 10 seconds. A short life, but a brilliant one. They can accomplish a lot in those 10 seconds. One thing they accomplished, and this is an experiment done by the MIT people, they took two separate condensates and they caused them to move towards each other. And when they overlapped, they saw fringes of high and low density, basically coherent constructive interference, destructive interference. It's fringes like this are something we're used to seeing in say two laser beams interfering, or a laser. You take a laser, you break it up, bring it back together. You're used to seeing fringes like that. But for atoms, to imagine that you take one chunk of atoms and another chunk of atoms and they interfere destructively, you know, atom plus atom equals vacuum. That's what those white stripes are, the vacuum where two pieces of atoms are canceling each other. I still find this amazing. If you take these two qualities together, that they are gelatinous, that they have a positive pressure, that they are coherent. These two things together predict that they should be a superfluid. If you were to take in principle, if you were to take a pipe and fill it with a Bose-Einstein condensation and take the two ends of the pipe and connect it together so you form a toroidal container and get the Bose-Einstein condensation flowing around inside this pipe, it would flow around inside this pipe essentially forever. It's a superfluid, the viscosity is vanishing. It's much like superconductivity for pairs of electrons, for current, for electric current, but it's like superconductivity, but it's superfluid for a massive fluid of a gas. It's difficult to do that experiment I mentioned. Instead, we can do it by looking at vortices. Here's a famous vortex. This one was in the Gulf of New Mexico, but obviously you're familiar with these, and if you live anywhere near the Bay of Bengal. And so these sorts of vortices, these cyclones observed from on high, always have a very low density core in the middle, and they move faster and faster as you get close to them. This is a classical vortex. It turns out that one of the easiest ways to see superfluid is to look for vortices, because if you stir up a superfluid, you see vortices, but they're quantum vortices. So we did experiments like this. In essence, we stirred them up. And we created, here's a ball of condensate, there's a little vortex, and this is time-lapse photography. You can see that over the course of the time, the vortex is moving around in here. Inside there, the vortex sort of orbits inside. You should think of this as a spherical ball of gas, which we're confining in a magnetic field, and this dot is a line. We're aiming down, we're taking a satellite image down the eye of the cyclone, and we're seeing, and this is how we're imaging the low density of the vortex. The vortex is a rotating field. It sees its own image in the wall of the condensate, and this causes it to move. It moves around. If you have cyclones, as we know, can come large or small. If the weather conditions agitate the air stronger, you could get bigger cyclones, bigger or smaller cyclones. The thing about vortices in a superfluid is that they come in only one size. If you stir it harder, here you see, if you stir it harder, instead of getting a bigger vortex, you just get more vortices. And if you stir it harder yet, you get more vortices or even more vortices or still more vortices. So this is the image, again, look down from the top. We're spinning the condensate so fast that the centrifugal force is causing it to expand. Instead of being a sphere, it is spread out into a dosa. Okay, it's big and flat and round, but very, very thin along the direction. And there are many, many vortices in it. And these vortices, if you see, are forming a beautiful crystalline lattice. This is because individual vortices find each other repulsive. And lattices are nature's way of putting repulsive things as far apart from each other as they can be. That's what makes a lattice. If we could put 100 cyclones into the Bay of Bengal, they would form a lattice there. This would be a very dangerous experiment. Obviously, we won't try that. And you can see here that I've put in these lines by hand, but just to emphasize that it's a perfect triangular lattice. And I think this image is, in many ways, a great way to head into the final stage of the talk, which is like, what are these condensates used for? What are they done? What are we doing with them now? And I think the answer is, this image we have here, besides being, in my opinion, a beautiful image, is a picture of a single quantum mechanical wave. It's a non-trivial wave. There's a lot of topological structure to it, but that is a single mechanical wave occupied by 1 million atoms. The atoms are doing a very elaborate, the wave function, it's a very elaborate, complicated dance as they weave their way around these vortices. But you are taking a picture of a quantum wave function, and we're not using a scanning tunneling microscope. This is just a regular camera with a non-heroic objective lens. The distance across here is a millimeter. So this is a single quantum wave, which is a millimeter across. You could almost resolve these individual dots with your bare eye. So this is the effect of cold, has the effect of taking quantum mechanics, which we think of as being very, very small, and expanding it into large, sensible dimensions that we can perceive. Why do we care about quantum mechanics? New technology, if the history of technology teaches us anything, new technology will be very, very small, and small is the place where quantum mechanics rules. So if we want to make progress in new technology, new materials, and so on, we really need to have a good understanding of quantum mechanics. If we want to build transistors or networks of transistors where the spacing between the transistors is short compared to the coherence length of the electrons, we better understand quantum mechanics, because we're going to see interference effects as they go through this pattern of transistors. If we want to design new materials similarly, this is supposedly this is our conception of a non-existent nano car. But still, again, understanding this nano car is an exercise in quantum mechanics. The rotation of these wheels is quantized. So are we saying that a Bose-Einstein condensation is small? No, on the contrary, the Bose-Einstein condensations at these very low temperatures are quite large, but compared to usual quantum mechanics, it's a millimeter across. But the ultra cold effect expands, magnifies the effects of quantum mechanics. So we can understand it easily, and when you can see things and all but touch them, it's easier to get a good intuition about it. And to make progress in technology, we need an intuitive understanding and not just a mathematical understanding. If I move forward and think about sort of Bose-Einstein condensation in the 1990s and 2000s, it's extended from alkalis to many species of atoms, and even to molecules have been made to Bose-Einstein condense. They're being used for precise sensing of acceleration. There are analogies to all the effects of optics we can do with waves of atoms, interferometers, super radiance, quantum optics effects of various kinds. You can think of the Bose-Einstein condensation, one of its features, one of its most in some sense, one of its least interesting features, but most useful features, is that it's very cold. And you could use it as sort of an industrial chiller. People who are trying to build quantum computers often start by making a Bose-Einstein condensation. So they start at these very low temperatures, and then their quantum computer, a Bose-Einstein condensate is a very coherent thing, macroscopically coherent thing. You need of many, many atoms. For quantum computers, you need individual atoms, not macroscopical samples of them. But you can embed those individual atoms in the condensate and have the condensate, essentially think of it as a chlorofluorocarbon, a chilling a fluid, a saltwater brine, however you want to think about it, some sort of cold fluid which is flowing over your quantum computer and keeping it cold. People have extended the work from bosons, atoms which obey Bose-Einstein statistics, to fermions, atoms which have a different internal spin and therefore obey yet a different kind, not Bose statistics, not Maxwell-Boltzmann statistics, but Fermi-Dirac statistics. It's possible also to make a sort of condensate in fermions, but you have to get the atoms to pair together into what are called Cooper pairs. And in this way, condensates in fermionic gases are a model, a large macroscopic atomic model for the nanoscopic effects of high TC superconductivity. That work was led actually by, if we go back to the picture of the people in the lab, here is a picture of a very young Debbie Jin back in 1995. She went on to establish her own lab, became a professor in her own right, and became the world leader, one of the most famous physicists in cold atoms and in condensed matter physics in the world, and did most of the pioneering experiments, I think, in fermionic atoms. Tragically, she died young, but she was an amazing physicist and a very good colleague and friend. And I dedicate this talk to her memory. And at this point, I think I've said all that I have to say, and I would be very, very happy to answer as many questions as you have. I have nowhere to go. So I thank you for your attention.
Thank you. Thank you, Professor Eric Cornell, for your wonderful talk. We enjoyed a lot, and we tried to see the details of inside how Bose-Einstein condensation can take place physically. That's a great thing to feel and to get to know how things are there. I think we may have my questions. May I request our technical team to take the questions through chat box and direct it to Professor Eric Cornell? Our technical team will take care of the question sessions. Have you got any questions in the chat box, which we can ask, we can put forward to Professor Eric Cornell? Can you hear me? Can you hear me, Professor Shams?
Yeah, actually, sir, till now we didn't get any questions in the chat box.
Oh. Then the floor is open. Anybody can ask a question, and Professor Cornell will be glad to address. If can I ask a silly questions, if you may think? What are going to be the uses, practical uses of this Bose-Einstein condensate that you have been finding experimentally?
Well, I think I tried to touch on some of these things. One is you could think of it almost as a very high-end teaching lab. As I say, it sort of is a way of understanding quantum mechanics at an intuitive level. This topic of quantum mechanics, many of us find very mysterious, but when you can actually see it happening, it becomes less mysterious, more intuitive. Also, I know there's some companies which are using interferometers where they take condensates, split the condensates up, bring them back together again, and they look at the interference fringes, and that pattern of interference fringes of alternating light and dark densities are sensitive to accelerations and to rotations. So you may know that in commercial airliners, they have gyroscopes which are based on optical interferometers where laser light travels around the fiber many times and then they interfere and they're very sensitive to rotation. Those are optical photon-based interferometers, photon-based gyroscopes. They're trying to make gyroscopes and accelerometers based on interfering atoms. The atoms having much more mass than photons are much more sensitive to inertial effects. So in principle, they could be more sensitive accelerometers, more sensitive, especially sensitive to gradients and in acceleration. So if you're walking along in a featureless desert and then suddenly gravity changes, say gravity becomes smaller, it's probably because there's something underneath of you which is less dense. Well, what's less dense than rock? Well, petroleum is less dense than rock, things like that. What else? I think these days, many of the people who were working on ultra-cold atom and Bose-Einstein condensation have moved into this field of using cold atoms as a model for quantum computers, for quantum information. So they use these same sets of techniques, laser cooling, evaporative cooling, and so on. Now, not so much to study a coherent superfluid, but as the fluid becomes coherent, they deliberately break it up into individual atoms and individually addressable atoms. They destroy the condensate in doing so, but they make use of one of its most notable features, its extreme low temperature. So, will quantum computers, quantum information ever become useful? I don't know. I know that a lot of money is going into it, and many of my colleagues have moved in that direction using the same combination of technologies.
Thank you. The technical team, I can see a few questions coming up.
Sir, now there are some questions. Sir, now there are some questions.
Yes, please.
May I first request Monish Debnath?
Yes,
Monish
please
Debnath.
go ahead and ask one after another.
Yes, first of all, Monish Debnath.
Oh, the
You
sound is not
raised
clear.
your hand.
Yes. Hello. Can you hear me?
Hello, Manish.
Hello, Professor Cornell. How are you?
Very good.
Well, it's a great honor to have the chance to talk to you, and I wish it have been a face-to-face conversation. I'm going to be honest with you. My question is not a technical one. It's rather a personal one. As I was reading through your autobiography provided at the official website at the Nobel Prize, and it made me chuckle when I got to the point where you mentioned about your first love, books, right? Hello? Okay. I'm sort of a big deal fan myself, and if I were given the chance, I would spend my lifetime only reading books and doing nothing. So my question to you is, if you were forced to read only one book for the rest of your life, and I know it would be a nightmare, which book would you choose?
Oh. Well,
it's a tough one, I think.
yeah. It's if I were to pick a single book to read for the rest of my life, I probably would want, it's not necessarily mean the best book. You want a book which has a lot of stuff in it.
Okay.
One of my favorite authors is an American author, Thomas Pynchon. He's an American author named Thomas Pynchon. He wrote several books, most famously Gravity's Rainbow, but also Mason and Dixon, Vineland. These books are extremely dense. You can read a page and realize that there are 10 jokes and you only got 5 of them. And this is after you've read the book 3 times. So I would probably read one. Also, his books are like 1,300 pages long. So I would want a long book with a lot of stuff in it in order to be, but that doesn't necessarily mean it's the best book. It just means it's the best book for being stranded on the island in the middle of the Pacific.
Sir, I have a question.
Okay. Thanks.
Yes.
Sir.
Who's talking?
Eric?
Yes.
Okay. So, Eric, when you showed that picture, the vortices, and you said the temperature was normal. So where did it condensate, and where did you see that vortice picture? Where the a beautiful picture, and all these vortices are spreading out and structured one.
Yeah.
So how did that temperature difference go? How did it go away?
I don't see your name. I don't see your picture. Who's asking?
I'm Sultana.
Sultana. Oh, Sultana. I'm sorry.
Sorry.
Yeah. Okay. Wonderful. Yes. We've communicated many times, but I have not come to recognize your voice yet. So for right now, I'm only seeing a couple pictures. Good. I misspoke. Actually, that picture was at extraordinarily low temperatures. That picture was taken at about 10 nanokelvin, and it was rapidly rotating. And it's in to make a picture like that, we spent a lot of time making, we keep the atoms in a magnetic bowl. And if the bowl is not perfectly symmetric, perfectly cylindrically symmetric, the rapidly rotating gas will quickly decay because they will excite these standing waves of ellipticity. So we put a lot of effort into making the bowl extremely round, and then we got the thing stirring, and we used the trick as the atoms were cooling down. We selectively removed atoms from the center of the trap. At the exact center of the trap, the angular momentum is 0. So if we take atoms from the center of the trap, it means we're removing atoms that have less than the average amount of angular momentum. And it's in many ways, it's the opposite of evaporation. To make things cold, we took atoms which have more than the average amount of energy, and that makes the average energy go down. To make them spin fast, we remove atoms which have less than the average amount of angular momentum. In fact, we take atoms from along the axis, high up on the axis, atoms which have high energy but low angular momentum. So the atom cooled, but also spun faster. And at the time we took the picture, the atoms were in a parabolically confining bowl with some frequency, a confining frequency of about 10 hertz. But the atoms were spinning at like 9.95 hertz, which is to say, if you're in a harmonic confinement and you spin, your rotation speed is faster than the harmonic oscillator, you just fly out, So we're flying, it was rotating within about 0.5% of the centrifugal limit of the fastest it could rotate before the centrifugal force would cause the atoms to fly out of the trap. And it was very, very cold. The image itself was a destructive image. What I mean by this is we turned off the confining fields, and the atoms, the gas expanded even further, so that we could better resolve the size of the vortices. It's kind of like taking a two-dimensional piece of rubber and stretching it out in all directions, and then taking a picture from above. So that gave us better resolution for the little vortices. But I don't know if I'm answering your exact question.
No, because you mentioned the picture was taken not at very cold temperature. So I thought, how did the whole thing is so low? Yeah.
Yeah, the gas was cold, but the camera, the lens, and the effect, the photons are coming in, and to make that picture, the photons have to be absorbed by the atoms. Sorry, the atoms absorb the photons and they make the shadow, and the act of absorbing that instantly heats the gas up and also gives them a big impulse. If we were to take a second picture, half a second later, we would see nothing. Basically, we have, of course, it's already a gas, but you could say that the energy of the image vaporized this thing. It totally destroyed it, only by making a very short flash of light, something like 2 microsecond flash. We take a picture and see it just in its glory, but also at the instant of its death. And the agent of the death was the photograph itself. The taking of the photograph, the heat from the photons rushing through the thing, heated up to essentially to room temperature. But because we take the picture very fast, we see a frozen image of the cloud.
So sorry, I have just one more question. Okay. All right. So you are showing those rings. Okay. This is the last one. I'll not ask. The rings, so like Newton rings we see in the experiment in our lab. So what kind of ring is that? Is that a photon? You said atom, or what is that? You know, the rings you showed, the, you know, the black and white image.
Oh, yeah.
The
Oh,
wave.
that's yeah. So if you we'll go back to that image. Yes. You know, if you usually time when you take photographs, you use incoherent light.
Yeah, this one. That's the
Yeah. Here. Yeah. Yes. Yeah. Usually when we take photographs, we're taking photographs with
after that, you passed it. If you go,
which way?
Newton rings in a, yeah, go, okay.
Down?
Okay, I don't know which direction.
After that.
Okay, go some, yeah, this one.
This one. Oh,
no, before
yeah.
that. Yeah, it's the
Before
same.
that.
No,
Here?
no, you passed it. You know, there are only two pictures. Yeah, this one.
This one.
Yeah.
Stop. Okay. So that is that's a different geometry. This is not a rotating geometry. This is two condensates are formed. They're independent condensates, and then they're released from their magnetic confinement, and they're gently pushed towards each other. And the condensates expand and they start to overlap. And we are looking, you know, down into it. And these lines here are actually planes. These are planes of low density. Basically, think of this as a cigar and another cigar, and the two cigars move towards each other along their radius and they overlap. And where they overlap, we see patterns of constructive and destructive interference, which are perfectly straight. And what this tells us, the fact that these lines are so straight along the entire length of the cigar, tells us that this condensate has the same quantum phase across the entire length of the condensate. And so does this one. If there were fluctuations in the phase, these lines would have wiggles in them. Does that help?
Yeah, so they are actually particles?
Well, they are, you're asking me, are they particles or waves?
Yeah, the particles from the waves when they condensate.
Yeah, well, they are atoms.
So this is a gas of sodium atoms, is it not?
Yeah.
Yes, this is a gas of sodium atoms. They are bosons. They have integer spin. And these are, you can think of this as a macroscopically occupied wave. The individual atoms are all participating in this wave, much as the individual photons participate in a laser wave. It's a time-honored question. Are these individual atoms? Or are they a wave of atoms? It's Charles, you can handle this one. You're a theorist.
There are now quite a few questions in the chat. So may I raise them?
Yes.
Yes. So Suraya Kazi, a question from Suraya Kazi is about the vortices formed in the condensate. What is the tip depth of the vortices? Do the vortices reach the center?
So the if I look at this vortex here, the density in the middle, in principle, should vanish. But this is actually what we're looking at. Really, this ball is very close to a spherical ball, and this line is a vortex line. It's a straight line. It goes all the way through the cloud from the face of the cloud, which is close to us, through the cloud into the back. And the density near the center of that vortex formally should be 0, because we have imperfect resolution in our camera. If we were to turn up the gain on our image here, we would see some atoms there, but that's probably because we're only just resolving. You know, we have imperfect imaging resolution. Also, it's possible that this vortex line, instead of being exactly towards our line of sight, the vortex line might be slightly tilted to one direction or the other, which will cause, for instance, as in this vortex line, to have it appear to be elliptical. It's not actually an elliptical vortex. It's just a vortex which is tilted a little bit with respect to the line of sight. So it looks, it has a, I don't know, is that, Soraya, is that the question you are asking?
Yeah. This is what I asked. And thank you for your answer. Yeah.
Okay. The next question is from Mamuna Rifat. Mamuna Rifat is asking, what is beyond Bose condensation state?
Well, you know, as we go, and beyond in my language means towards lower temperatures. I think of beyond as, you know, that's the direction where I think of beyond goes. And as I mentioned earlier, to go to see, for instance, pairing of these fermions, having the fermions pair together and form a condensate, one has to go to a lower temperature, a lower scale temperature compared to the density. So one answer is what's called a BCS state, the Bardeen-Cooper-Schrieffer state of fermions of very cold atoms. As you go colder yet, things like we have something called a Mott insulator, which is a state of matter which is predicted and observed in condensed matter physics, solid state physics. I could say, but has been observed in gases and in ultra cold gases. There are various. As you get colder and colder, the individual atoms are like little magnetic dipoles, and as it gets even colder, the little magnetic dipole force of one atom starts to interact with the little magnetic dipole force of the other atom. And you could get, especially if you confine the atoms into a sort of lattice-like structure, you can get very exotic magnetic, antiferromagnetic, ferromagnetic states. These require extraordinarily low temperatures, much lower than these temperatures, especially if you scale the temperatures by the density. So I would say still more generically, the answer to your question is beyond Bose-Einstein condensation is still more exotic states of matter, many of which have some analogies in solid state physics.
The next question is from Pritam Kumar Das. He is unmuted. Would you like to ask your own question?
Thank you, sir, for giving me opportunity to ask question. Thanks, Professor Cornell. Sir, thanks for giving us opportunity to ask question. So it's a great opportunity for us to learn from you directly. So I have one silly question. It may be very silly. So can BAC drop be used as a laser beam instead of light?
You know, it can be used as a thing which has many things in common. Oh, there you are. Hello. You're just appeared. It has many things in common with laser light. I should emphasize that it does not travel at 300,000 kilometers per second. It travels at a few millimeters per second. So it's much, much slower than light. But it has things in common. For one thing, the way it forms, the way a laser beam forms is via stimulated emission. Atoms stimulating photons, excited atoms stimulate photons into an existing mode. And there's a very close analogy of the formation of the condensate. You start with a small number of atoms in a mode, and then other atoms collide, and there's an enhanced probability of atoms scattering into the macroscopically formed mode. And it forms sort of a gas which is supersaturated, which is a very close analogy to the idea of your atoms being, your lasing material having an inversion, having the excited state more populous than the ground state. The analogy with that in Bose condensation is the gas is a supersaturated gas, which means that it really wants to decay into a condensate. So there are many analogies. You can, it's possible to, in essence, you have a bowl of atoms. It's possible, in essence, to open a little hole in the bottom of the bowl and have atoms fall out of the bowl, essentially under the influence of gravity. And then you actually have a beam of coherent atoms traveling down. You can use, and you can see that it's coherent because you can split the beam up and split the beam into two beams and have them come back together again, and you see beautiful interference fringes. So I guess the short answer is it has a lot in common with a laser beam, and the physics of its formation have a lot in common with the physics of laser formation, as it should, because what are photons? Photons are bosons. This is an image of rubidium atoms. What are rubidium atoms? Rubidium atoms are bosons. They obey a lot of the same statistics, a lot of the same quantum mechanics.
Okay, sir. Thank you.
Muhammad,
May I
Jamil?
pursue the optics analogy, but with reference to a figure, something very wonderful about that figure that I think addresses the previous question.
Go ahead.
Something I only, sorry, the three-peak figure with the release profile at different temperatures.
Yes. Where is our three-peak figure? Oh, there it is. Yes.
No, the one with just the expansion profile of the original, the three mount. Yes, this one here. So there's something really wonderful about this figure that I think I learned from you, and when I heard it, I realized how beautiful it is. The cloud has been released from a pancake-shaped trap on 3 separate occasions. And one might think that the pancake, these sharp peaks, is the shape of the pancake, but in fact, the pancake is in the perpendicular direction, because it's the atoms that are more tightly confined by Heisenberg's uncertainty principle expand more rapidly. So you see, in this expansion profile is an inversion. This expansion profile is an inversion of the original density profile. And that's very much like what you see if you think about light going through an aperture. Coherent light that goes through an aperture will diverge in the far field. So if you have incoherent light going through an aperture, its profile is fairly steady in the far field. It just shows us a circular expansion. But coherent source shows this different peaking, which is again due to the uncertainty principle.
Yeah, that's very well put, Charles. And historically, my students came to me and they said, look, we see this broad distribution, and then we see a broad distribution with a narrow distribution in the middle of it, and then we see a narrow distribution. This must be a Bose-Einstein condensate. And if you're someone who supervises graduate students, you're always suspicious, not because you distrust your graduate students, but because you know they want to bring you something that will make you happy, because the graduate students want to make their advisors happy. So when it came, I was going, this makes me very happy, and therefore I can't believe it. Like, I can't allow myself to believe something that makes me so happy. And one of the things that came to us is, if we look at this cloud, it's essentially circular in cross-section. The thermal part of this cloud, the skirt down here is circular. This part is elliptical, and this part is purely elliptical. And we knew, just as Charles was saying, is that it was coming from a trap with the opposite aspect ratio. It really speaks to this non-condensed atom as being basically just distributing in a purely thermal way, this part of the cloud being thermal, this part being coherent, and now this part being purely coherent. This aspect ratio was not something that I asked my students to bring me. They brought it to me not knowing that it would make me even happier. So it's always sort of nice to have it was one of the things that at the time, it was a very exciting moment, and it's so easy in experimental physics to fool yourself. I've done it many times. Hopefully I haven't published that very often, but certainly there have been days when I thought, oh, this is amazing. And then the next day I think, no, it's not so amazing. And I thought that this aspect ratio that Charles has pointed out was something that gave us a lot of extra confidence.
There is a question
Shams,
Muhammad Jamil. There are two
questions. Two more. They are the last. They are the last questions.
Okay.
We will not entertain anymore because the time is over, and we have to close this session. So these are physics.
Yes, two more physics questions I can see here. One is Muhammad Jamil. You are unmuted. Would you like to ask your own question?
Yeah, I am thankful to the professor because I got the answer from Muna's question. I am thankful.
Okay. Next.
Hi, I have a question to the
yes.
to this.
Yes, Dr. Muhammad Azizur Rahman. Yes,
Yeah,
now.
yeah, Professor Eric, Cornell. I have the question is how is it possible to produce so low temperature of the order of nanokelvin?
That is what is the main thing.
Yeah, well, the important thing, you need to do a few things. You need to have very, very good insulation. Obviously, the environment at 300 Kelvin, and only 2 centimeters away, we have something which is 9 orders of magnitude colder. So our vacuum is extraordinarily good. The
Yeah,
other thing that helps us get to that low temperatures is the atoms. Oh, this connects to the beginning of the talk. You know, inside our chamber, there's black body radiation, photons at 300 Kelvin, but atoms do not absorb at that wavelength. The black body radiation is at 30 microns, 20 microns, and that passes all the thermal radiation. Like when you go out in the sunshine, you feel warm. That if you have a gas of atoms, that warmth passes directly through the atom, vanishing, no absorption whatsoever at that wavelength. That helps. Finally, we need a mechanism, which in our case was this evaporative cooling I discussed, which is just something which works. You know, we confine the atoms in a magnetic field, and you know, you can only do that if you start with something which is very cold. If I just take you know, oxygen molecules are magnetic, but if I go to my refrigerator and maybe I have some, you know, a postcard is stuck to my refrigerator with a magnet. So if I take off that magnet, it's maybe so long, I hold it in the air, the oxygen does not stick to the end of the magnet because the oxygen is at 300 Kelvin in my room here. It's going very fast. It's not impressed with my magnet. So we have to use first the laser cooling I mentioned to get things down so they're moving slowly enough that the magnetic fields are able to have some authority over them. And then we could build the magnetic moles, and then we could do the evaporation. So many steps. Any one of these steps we didn't invent. You know, Carl and I did not invent laser cooling, did not invent evaporation. We did not come up with the idea of Bose-Einstein condensation. Instead, we just lived at the end of the 20th century when there were many good ideas around, and we were not too proud to steal them.
Oh, thank you.
Thank you.
By the way, sir, I just want to make a note that the last questioner, Mohammad Jamil, I think he was from Pakistan. So it's good.
Good.
Okay, that's the last question.
No, he has already asked his question. He said he got the answer.
Answer from Mohammed, yeah.
But I just wanted to point out because with everyone speaking in English, it's often difficult to note who is from where. But he was from Pakistan, so that shows the reach of this conference.
Very good. I'm glad to hear that.
We are glad that people are joining to this conference from everywhere, from Bangladesh, Pakistan, America, and others. That is the purpose of our conference. Anyway, we have come to the end of this plenary session lectures, and we had heard from Professor Eric Cornell a wonderful lecture, and there were many questions which he answered, and we are really grateful to you that you have come to attend this, to give us lecture in this conference, and our students and researchers will be inspired by this. Let us give Professor Cornell a big hand and say goodbye.
Okay.
Thank you, Professor Cornell, and thank you, the organizers. We have come to the end of our sessions today. We shall see.
There are more participants from Pakistan.
Right, that's great. It's good to hear.
There are more participants from Pakistan. Some Rifat was responding to it.
Very good to hear. That's nice.
Yeah.
That's nice to hear. Thank you all of the participants and the listeners who are audience who have joined our e-conference here. We are thankful to all of them. We shall see you. We shall meet you again tomorrow when the session will start right at 7 p.m. Bangladesh Standard Time. Thank you, everybody. Thank you.
When is that?
7 p.m. Bangladesh Standard Time. 7 p.m. Bangladesh Standard Time, like what we have today.
Yeah. Thank you.
Thank you. Thank you, Eric. Once again, I hope you will bring you here to Bangladesh once in next.
Okay.
Very soon.
See you all.
We
See
look
you all.
forward to meeting you. Thank
Very
you.
good. Bye-bye.
Thank you.
Thank you.
Bye-bye.
Bye. Sultana, is it okay that we close it down now? Nozul, do you have anything to say? Nozul?
Sultana, you are muted.
Okay, sorry. Eric, I just want to say, please come to the valedictorian session on Sunday.
Of course. Yes.
Okay. All right. Thanks.
Thank you.
Right.
Thank you.
Thank you, sir. Thank you all.
Thank you.
And Allah Hafiz and bye.
Allah Hafiz. We had a
Thank you
very
all.
fruitful session
Very
today.
successful one.
Thank you. Thanks. Thank you. Bye.
Bye-bye.
Bye, everybody. Allah Hafiz.
Allah Hafiz.
Assalamualaikum, sir. Sham sir, very well done, sir. Excellent technical committee.
মাঝে সমস্যা হয়েছিল, আমি একটু কিছু সময়ের জন্য আমি আউট হয়ে গেছিলাম।
কিন্তু কেউ বুঝতে পারেনি স্যার, খুব চমৎকার ভাবে ফার্স্ট টু লাস্ট গেল উইদাউট এনি ট্রাবল।
প্রফেসর শামস ভালো আছেন?
জি জি আছি।
তার ফেসবুক থেকে কোনো প্রশ্ন পাইনি, আমি বেশ কয়েকবার তাদের জিজ্ঞেস করেছি যে ইউ ক্যান রেজ ইউর কোশ্চেন হিয়ার, আই উইল ডেলিভার টু দ্য স্পিকার, বাট নোবডি রেসপন্সড।
এটা যে প্রশ্নগুলো এসছে লেট আর কি, মানে প্রথমে নাই, তারপরে হঠাৎ করে।
স্যার একটা পয়েন্ট আপনার নজরে আনি স্যার, শামস স্যার, আমার মনে হয় ওই যে আমাদের প্রফেসর ডক্টর জাহিদ উনি প্রেজেন্ট করার পরে আমাদের মামুন স্যার এবং সালে নকিব স্যার দুজন হাত উঠিয়েছিল, তো ওনারা বোধহয় প্রশ্নটা করতে পারেনি, মানে স্যার বোধহয় ওনারা বোধহয় সুযোগ পাননি, তাই না স্যার? মানে টাইম
সুযোগ পাইনি, তাদের সুযোগ দেওয়া হয়নি, দেওয়া হয়নি সেই সময় দেওয়া হয়নি।
দুজনে হাত উঠিয়েছিল এবং আরো কয়েকজন, কিন্তু প্রফেসর জাহিদের কাছে আরো কয়েকজনের কোশ্চেন ছিল আমাদের চ্যাট বক্সে।
ওই সময়টা আমি হয়ে গেছিলাম আর কি, তো কিন্তু আর কেউ আপনারা বলতেন যে উনি
স্যার, মানে আমি বলবো যে ম্যাচ বসানো তো চাচ্ছেন না, মানে স্যার হয়তো টাইমটা মেইনটেইন করতে চাচ্ছেন।
May I ask a question, please? Because this